Okay, let's move on to the another topics. So, in this lecture, we will talk about the debugging of learning algorithm. Okay, suppose we have implemented the regularized linear regression algorithm. This one. However, when we test your function on your new input, let's say the testing dataset, you find that it makes unacceptably large errors in each prediction. So then, what should you try next? Okay, the good machine learning algorithm should predict the stable output even for the new input, right? But in this case, it has a low generalization power. So generalization means our machine learning algorithm have to or should produce the good prediction even on the new input or even on new testing data set. So, but if we can't do that, so it has we say that it has a low generalization power. Then how can we overcome that? How can we improve this? There are several things we can do. The first of all, actually this is a very this is the most easiest way to solve this problem. Get more training data set. As we see the previous slide, if we have the more training example or training data set, we have a high probability that model the distribution of the training set. But at the same time, the get the high more training data samples really hard to get it because it is the labor intensive and it is hard to get it. So actually it's not a good solution. So another way is to use the try smaller set of feature because if there is a generalized problem, we could say that there are some kinds of redundant features, so we can use some optimal set of the features than the every features. Okay, or try to get additional features like the okay. Let's say we have the feature x1 x2 something like xn to improve our machine learning algorithm, we can use the additional training sample, something like that. It means that okay, we can find a new feature for our machine learning algorithm. So that's what we can do. So another thing we can do is try adding polynomial features like x0 square x1 times x2 something like that. So by using some kinds of polynomial feature, we can improve the model capacity or the model complexity. But at the same time, there are overfitting problems. So we have to be careful to choose the polynomial feature, or try decreasing or increasing the the regularization parameter or the penalty parameter, right? So we can adjust this parameter, right? So that is we can do. Okay, wait a minute. What's that? Okay. Okay, let's continue. So okay, here is a new concept: machine learning diagnostic. Diagnostic is called a task that you can learn to gain insight what isn't working with a learning algorithm. So it can provide some guidance to learn how best way to improve the each performance. So it's called the diagnostic way to our machine learning algorithm. So diagnostic can take some time to implement, but doing so can be the very good use of your time. So by using some kinds of diagnostic technique, we can improve our machine learning algorithm, even though we use the same same mapping function or the same parameter. Okay. So today we're gonna talk about what is the machine learning diagnostic. Okay. Before that, let's see the example first. Okay, let's say we have a training data like the size of the house and price of house. Let's say this is xn, this is yn, right? So this is the examples of the linear regression problem, right? But comparing to the previous one, in this case, we want to divide the training sample or our samples as a something like that. So what does it mean? In this case, we can use these kinds of samples as a training data, and we can use this remaining one as a testing data, test set or the test set or test data. Let's say we can pick the 70% of the samples as a training set and the 30% of the samples as a testing set. Then let's say this data as a like this. So this notation means the first sample, and this is second sample, something like that. Anyway, this is the training set, and we can determine the testing set that represent looks like this. So yeah, so what we want to do is when training our learning algorithm, we just use these samples, and then we do not use this sample. Then after training, in the testing phase, we just use the testing samples to diagnostic our algorithm. What does it mean? It means that if we use the testing set, we can determine our machine learning algorithm have a good generalization power or less or weak generalization power on the real data set. Okay, so that's the simple way to determine the generalization power or diagnostic the generalization power of our machine learning algorithm. Okay, here is a formal here is a formal definition. Okay, let's see the linear regression problem first. Training and testing procedure for linear regression problem. First of all, in the training page, train the machine learning algorithm with the parameter W from the training data, using only training data, using only this one. In other words, just minimize the training error here on the training data set. And then after training, we can use this parameter here to compute the tested error. Here is the new error like this. Actually, this is the exactly same as loss function in the training phase, but at the testing phase, let's say testing phase, and this is done in training phase. Okay. So at the testing phase, we did not optimize this W anymore, but just compute the error to know our machine learning algorithm with the parameter W has a good generalization power or not. So in this case, the W is fixed. Okay. In another case, like the logistic regression problem, we do the similar things like this. Train the parameter W from the training set, or minimize the training error with a cost function, and then using the train the parameter W here, we just compute the testing error using this logistic regression function or logistic regression mapping function. Okay, so in this case, similar to the linear regression problem, the W is fixed, right? And just compute the error, test the error. Okay, then we can determine that machine or that parameter have a good generalization or not. Okay, or there is alternative way to use the misclassification error. For example, rather than using this one, we can just compute the misclassification error as a 0 or 1, or call the positive or negative, right? So if the class has a good approximated value, it has a good classification. But let's say, okay, let's see the example. Okay, y test sample 1 was a 1, y test 2 was class 0, something like that. And okay, let's say estimated 1 was 1, and estimated 2 was, let's say, in this case, this sample has a good approximation, right, or good prediction. But in this case, it has a long prediction, right? Because it should be 0, right? So in this case, this is the misclassification. So by measuring the number of the misclassification samples, we can just compute the misclassification error. So this is another way to estimate the error. Okay, so this is a way to diagnostic. Here's another way. So okay, let's go back to regularize the linear regression problem, such that it has a original loss function with some regularization term like this. So the goal of the machine learning or the linear regression is to what? Is to choose W, or is to find the W to minimize this function, right? So this is the goal of the linear regression problem. Okay. Then how can we control the performance of the machine? How can we control the performance of the machine? There are two kinds of things we can do. First one is we can adjust the penalty parameter lambda here. As we see previous slide, we can adjust the penalty parameter lambda to adjust the performance of this linear regression model Or we can adjust the model complexity. For example, degree of the polynomial features or other model complexity. So there are two kinds of things we can do, right? Then let's say these two kinds of thing as a hyperparameter. Let's say lambda or the degree m, something like that. Then how can we choose the best hyperparameter? This is the problem of model selection problem. So model selection problem means to find the optimal hyperparameter in the machine learning algorithm. So okay, let's see the model selection. What is the model selection problem? Okay, so yeah. This is the same page. Sorry about that. So first thing we can do is just use the grid search algorithm. What does it mean? Okay, let's start from the very simple mapping function like this one. Okay, so in this case, the degree of the polynomial term is 1, right? Let's say this is degree t or m. We can use any kinds of things anyway. So, or we can use another mapping function with the degree of polynomial is equal to 2 or 3, in this case 10, something like that, right? So okay, degree of polynomial. Okay, so first of all, what we like to do is to compute the test error. The test error, this one, for those kinds of case. So let's say this is the test error. Let's say like this. This means degree of freedom. Degree of the polynomial term. Okay, let's say degree. And the current case, L test W2, right? And in this case, L test W10, right there. And then just choose the minimum values, minimum test error, to determine which parameter set or the which mapping function is the best. So in this case, the L, let's say L test W3 was the optimal. So then we can choose this mapping function as our model. Okay. So, but here is a problem. This L test W, this the error of the test set is likely to be an optimistic estimate of generalization error. That is our extra parameter is fit to the test set. But here is the problem. Actually, in most cases, it's really hard to get the testing set, right? We only have the training set and we don't have the testing set. Let's say, for example, if we train our machine learning algorithm and test this model on our new algorithm, new sample. Let's say the today's sample. We don't have the label or the ground truth yet, but we want to find the solution, or we want to estimate the solution. But in this case, we cannot access the testing set before training the data. So in this case, we cannot use this technique or this strategy. So we need another strategy. So that's why we introduced the cross-validation set. What is a cross-validation set? Okay, compared to the training and testing set, we want to introduce a new set of training sample. First of all, let's divide the previous training set samples as a training set as a cross-validation set, or just say validation set and test set, right? And each samples generate the each set of the samples, something like that. Let's say just pick the 60% of the sample and 20% of sample as a validation set, and 20% of samples as a test set. Okay. So in this case, we can do the similar thing like this, just using the training set and validation set. So it means that we don't need to the ground truth testing set to determine the generalization power of our machine learning algorithm. So that's why we introduced the cross validation set. Okay, so in other words, okay, let's define the training error until like this. This is exactly same as the loss function for the linear regression problem, or just regression problem. Okay, so this is the ground truth samples in the ground truth output in the training set, and this is the estimated value of the input x in the training set. Similarly, we can define the close validation error or test error. The main difference is here. We define these three kinds of the errors on each set. Okay. Okay. So this is the training, validation, and test error. Okay. So let's see. Sorry about that. Sorry about that. Yeah. Yeah. Okay, let's move on. So here is the here is a new way. So okay, this is the previous example. Now we can measure the error on the. Okay, let's use the red color. Okay, now we can measure the error on the cross validation set, like this, like this. So, and then estimate the generalized error for the test set. So this is a more efficient way to see the generalization power. So this is called the model selection. Okay. Okay, the last concept is the bias and variation. The term of the bias and variation is different depending on the problem or the context. But here in the overfitting problem here, bias and variance are defined as follows. Okay, let's see the example. This is the same example in the previous slide, right? So, okay, we have five training samples, and we have a size of the house and price of the house. Okay, let's say there are three kinds of candidate, the mapping function candidate. The first one is the first one is the when d is equal to 1, then the second one is d is equal to 2, the third one is d is equal to 4, right? So in this case, the optimal shape of this model is looks like this, or looks like this, or by using the higher dimensional polynomial term, we can estimate the mapping function. Looks like that, right? Something like this. So in the previous slide, we said that this is the underfitting problem, and this is the what we want to do, and this is the overfitting problem, right? So now we want to introduce a new terminology, say bias and variance. What is the bias in this context? In the underfitting case, we say that it has a high bias. It has a high bias to the training sample. So this is a high bias case. And in the overfitting case, we want to say that it has a high variance. High variance. So what does it mean? What does it mean? So underfitting problem is the high bias to the sample, and overfitting problem has the very variety mapping function shape like this. So this is called the variance and bias. So then how can we say that? So in this case, we can say that this has a low variance, right? And this case called the low bias, right? So there is a trade-off between bias then variance. Actually, there are some definition or the equation related to the bias and variance, but in this course we just learn the concept of the bias and variance. So in other words, the good machine learning algorithm to overcome the trade-off between the bias and variance problem. Okay, so this is the definition of the bias and variance. So let's see the example. Okay, let's say we have a training error or the training loss function, something like this, and testing error or the testing error looks like this, or the here we can say that close validation error, because we assume that we don't have the testing set yet. Anyway, so here is a two error. So what we want to do is to see the shape of the error as bearing the degree of the polynomial term. Let's say d in the mapping function. In the mapping function here, because it was the d1, d2, d3, d10, right? So what we want to do is we want to plot the error as bearing the degree of the polynomial d, right? So First of all, okay, here is the d is equal to 1, here is d equals 2, here is the, let's say d is equal to 10, okay? So, do you remember the shape of the when t is equal to 1? It was looks like this, right? Then what about t is equal to 10? It was looks like this, okay? Okay, so it means that when t is equal to 1, there are some errors like this in the training sample, but when t is equal to 10, there are limited error there, or there are no training sample error, right? Something like this. So we can say that the shape of the error in terms of the degree of the polynomial looks like this. So we can say that this is L test W, like that, right? Then what about the cross validation error? What about the cross validation error? We already know that if there is an overfitting problem like this, the generalization power is limited, right? So what does it mean? As varying the degree of a polynomial, the cross validation error are decreasing, but after some point, it will be increased like this because of overfitting problem. So let's say this is the cross validation error like this. So yeah. So actually, this one and this one is not this one and this one is not a good shape that we want to get. So actually, the good machine learning algorithm or the good method should provide the lowest error on the cross validation set. So it means that here, this point, let's say t is equal to 5. So this case is the most proper case of our machine learning algorithm. So there is some trade-off as varying the polynomial d. Okay, so let's see the detail. What does it mean? Okay, so in other words, okay, suppose your learning algorithm is performing less well than you are hoping. It means that we have the high cross validation error or the high testing error. Okay. So is it a bias problem or the variance problem? Okay. Okay. Let's read through this plot here. Okay. So this is the training error as varying the polynomial d. Yeah, this is the training. Okay, right? And this is the cross validation error. Okay, cross validation error, and this is the testing error. Okay, so let's say here is the d is equal to 1, and here is the d equal to 10. Okay. Okay, so let's see this one first. Okay, so when t is equal to 1, do you remember? Oh, where is that? Okay. Where is that? Yeah, here. So when t is equal to 1, it was the high bias problem, right? So when t is equal to 4 or the much higher value, it was the high variance, right? So if you remember this page, in this case, train errors will be high because this is underfitting problem, right? And L cross validation error is similar to the train error, like this case. So it's not desirable, right? Because not only the training errors high, but also validation errors high. So this is called the bias problem or the underfit problem. Another case is that L train W will be low, but L cross validation error much higher than the L train W, like this case, right? In this case, L train, the error on the training samples is the lower, but the errors on the cross validation set was much higher than the errors of the training set, like this one. So in this case, this is called the bias variance or the overfitting problem. So actually the most proper machine learning algorithm should provide the best cross validation error here. So that we want to solve. So we want to we want to find the good solution, something like this. But if there are some generalization problem, something like that, we have first of all we have to diagnose this is the bias problem or this is a variance problem. Okay, so this is the diagnosing bias and variance. Okay. Okay, so then how can you solve this? How can we solve this? Okay, let's see the example. Okay, let's say we have a mapping function or the model, something like this. Okay, so there are 4 kinds of term with a constant value. So in this case, d is equal to 4, right? So in this case, our regularized linear regression problem is described something like this, right? With some kinds of regularizer here, with penalty variable lambda, like that. As varying the penalty parameter lambda, actually we can adjust underfitting and overfitting problem, or the high bias or high variance problem. Let's see the example. Let's say if we use the large lambda here, then the shape of our mapping function will look like this. Why? Because in this case, W1, W2, W3, and W4 will be the approximately 0, and there is only, okay, let's see, there will be only constant term, so something like this. So if we have the very large lambda, it generates the high bias and underfitting problem. Or if we just use the small lambda value here, right? In this case, we will ignore this term, just minimize this cost function, that it generates some kind of overfitting problem as we discussed previously, something like that. So it will generate the high variance or the repeating problem. Then by using the intermediate lambda or the proper lambda value, we can just write the mapping function. Something like that. So that's why we have to pick the best value for the lambda. Okay. Then how can we do that? Similar to this one, we have to pick the regularization parameter lambda using the grid search. Try the as much as possible lambda values. When lambda is equal to 0 and lambda is 0.01, 0.02, or when lambda is 0.10, something like that. Then what should we do? Compute the cross-validation error. Something like this. In this case, in this superscript means the second trier and the third trier. Okay. Anyway, let's something like that. And pick the best values or pick the best one as our final number. So this is the kind of the cross validation. Okay. In other words, unlike the machine learning parameter W1, W2, W3, something like that, hyperparameter lambda, we cannot train these lambda values during the training page. During the training page, we just find the optimal W0 or W1, but we don't know what is the best solution of this lambda value. So that's why we have to think about cross validation technique to pick this number. Okay. So this is called the cross validation. Actually, in the recent paper, there are several kinds of solution, not to train not only this parameter, but also this hyperparameter. So recently there are several papers, but in this course we just say that this lambda values as a hyperparameter. Okay. Okay. Let's see the hyperparameter. Okay, so yeah, we can draw the similar plot like this as bearing the regularization parameter lambda. Okay, so here is a training and cross validation errors. We want to consider this penalty parameter. Okay. So first of all, as bearing the lambda values, so the shape of the errors looks like this. Okay, let's say this is error. Why? Small lambda and large lambda. If we just very large lambda, right? If we just using very large lambda, the model is just biased to the constant value, right? So in this case, there will be the very large error here, right? So that's why the shape of the train error looks like this. However, when we draw the errors of the cross validation, it will be looks like this. Okay. Why? 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 Why the cross validation error looks like this? Because when we just use the small lambda here, small lambda, so it will be OPT looks like this. Then the training errors will be the small, but there will be the very large cross validation error. So let's say, okay, this is cross validation error. So this is a train error. Okay, so this is the just right we want to solve. And in this case, this is the bias. And this is the what? Variance case. Okay, so as varying the training regularization parameter lambda, there exists the bias problem or the variance problem. Okay. Okay, so the last one is the high bias and this was high variance. High bias and high variance. If a learning algorithm is suffering from the high bias, getting more parameter, getting more training data will not help much. What does it mean? Okay, as varying the training training set size, the training error will be looks like this. But the model has a high bias. The test error or the cross validation error will be looks like this. So what does it mean? So in case of the d is equal to 1, the mapping function looks like this. But if we increasing the number of samples like this, the shape of the mapping function still looks like this because we are just using this linear term. So it means that as getting more training data, we cannot improve our model, right? So this is the limitation of the algorithm that suffer from the high bias problem. Okay. Another problem, high variance problem. So if our learning algorithm is suffering from the high variance, getting more training data is likely to help. Let's say maybe help because it's not necessarily means. Okay. In this case, as increasing the training set size, the loss of the training set looks like this. Let's train, and let's say this is the cross validation error like this. In this case, when we use the higher degree polynomial term with a small lambda, we can fit this data set looks like this. But as varying the training set, we can still fit the data set looks like this. So it means that okay, as increasing the training samples, we can improve the chance or probability to fit the real linear distribution of the, this is called the linear distribution. Linear distribution of the sample, because they have the high capacity, right? So it means that so carrying more training data is likely to help in case of the high variance. Okay, so this is a high bias and high variance case. Okay, so let's go back to the our problem. Okay, so in the first page of this lecture, we were talking about the debugging or learning algorithm. Okay, we have a, suppose we have implemented the regularized linear regression or the machine learning algorithm. However, when you test your function or your machine learning algorithm on the new input, you find that it makes unacceptably large error. So it means that it has a low generalization power, right? So what should you try next? First of all, get more training example. Get more training examples means mapping this one. You fix the high variance problem and try small set of feature will fix the high variance problem, right? Let's say problems we're here, right? And you try getting additional feature is going to fix the high bias problem. Adding polynomial features is going to fix the high bias problem, and try decreasing lambda to fix the high bias problem, and try increasing the lambda fix the high variance problem. So these answers are related to the this one, and this one. So please summarize this kinds of the answer yourself, okay? With this figure and this figure. So it will be the good debugging method for your new algorithm. So